Good afternoon to all of you. Welcome to my tutoring session, my science session. I'm here for you to answer science questions you may have. Tonight's topic, or today's topics, will be about some missions that NASA is sending into space for moon exploration. So we'll talk about astrobotics, and the other one is Artemis 2 that has been delayed. And we will also talk about optics. I have a student who wanted to have more information about optics. They are having their grade 10 science exam here in Ontario, here in Canada, and therefore I'm going to do a quick review on the key topic for you. If it happens that throughout the show, if you have any questions related to science, don't hesitate to put them into the comments below. I'm here to answer questions you may have. So on this, let's see if we can look at the first topic today. So interestingly enough, we have had, so let's see if I can present my show. So Windows, we have this one here, and share. So let's see if I can, I'm going to do this and this. My first topic today is about Astrobotic. It is a company that is specializing in sending equipment and sending some probes around the moon so we can advance science. So let's see what information we have about them this week. So first of all, if we look at the information we've got, so this is the map of what we know about the Pelegrine Mission 1. We know that it left here, I think it's January 8th, went around the Earth here. The big issue we had is that we had issues with the engine to send the probe into space. So the issue we had is that there was a malfunction, and then people thought, well, will this mission be able to survive? So here, from this point here, we had some difficulties. They had issues with power because they could not align the probe towards the sun to recharge the battery after the takeoff. And they were able to do a whole bunch of different updates to the machines. We had engineers on the ground, and they were able to salvage some of the mission. So what we know is that we are since the 8th, so 4 days in, we know that the probe was able to go, and here is around where the orbit of the moon is. Keeping in mind that the moon is coming closer, so the plan is for the probe to come back here around Earth, and then come back around here around the moon and be able to be caught around the moon through the moon's gravity. So here what we have is we have a mission, and we have I think it's 12 of the 20-ish pieces of equipment that are working right now. So the battery is fully charged. They were able to align the probe. So we know that at least 12 of the pieces of equipment is working. It's information from the wind, from the sun, radiation, everything to collect data to know, to make sure that the astronauts going to the moon in the next couple of years will be safe. Now, the issue, though, is that once they had difficulties with the takeoff, they realized that there was a helium tank that was leaking. And the issue with that is that it created a situation where they had less energy to power, or they will have less energy to power the probe. So that means that the probe will be able to go around the moon to get telemetry, to get information that all the onboard equipment is supposed to work. However, they don't have enough energy to safely land the probe on the ground. So if you look here, this is one of the image from the company here, and I'm going to put the links in the video below so you'll be able to go to them if you wanted to check. And here we were supposed to land here the probe onto the moon, and here from there we have, I think the name of the rover is Viper. And what happened is that they were supposed to go and check for water on the moon, check for some radiation, check for a whole bunch of different parameters to have the astronauts going to the moon safely very soon. So if you go here on Twitter, and I'll put the link here below, we know that the Peregrine probe is now at 238,000 miles from Earth. It's working The telemetry is working well, very nice, but the engineers are still optimistic about extending the life expectancy of the probe. Now that it's not, they agree that it's not going to be able to land on the moon, so they're going to try to see, is it possible once it's in orbit around the moon, be able to gather data. So if you were to go on their X account, so they've been having several updates a day to tell us what was going on. Very nice. Very good, very good, very good. Now, this created a situation though, because very nice. Now that the data collecting still can happen through the probe, now NASA will be able to gather the needed information. The problem though is that we're planning to send the Artemis 2 mission for the 4 astronauts around the moon. And there's been a lot of plans for 2023 and 2024. However, not being able to send a probe on the moon, that means that we will not be able to have all the information to make sure that we have the safest landing of astronauts on the moon in 2025. So that means that they have changed. They wanted to send possibly astronauts in 2024, 2025, and now they have changed the launch day. And the reason for that is they're saying that knowing that the previous launch here of Astrobotic did not quite work well, then they need to make sure that this mission is stabilized, trying to figure out what happened to when they launched the probe, but also not being able within 2024 to collect the needed information on the surface of the moon. They decided for safety to postpone the Artemis 2 mission. So is it disappointing? Yes, it is. However, we are thinking of the safety of our astronauts. Keeping in mind that if you think 50 years ago, when we were sending astronauts into space, the rockets were not as well built. The potential for malfunction was so big, but they trusted the system and many missions worked very well. However, in 2023, we want to 2024 right now, we want to make sure that all people will be able to be safe when they go. So this is quite important in space exploration right now. Another piece of information that is kind of nice is that on my French channel, I talked about the fact that we had OSIRIS-REx probe that went to the Bennu asteroid in the last many months, and then came back with a sample on Earth last year. So what happened is in the last few months, they've been working on the sample container, the canister that brought back the sample. Now, interestingly enough, it seemed that as they were trying to get inside the canister to get the sample, it seems that there were 2 rivets that did not quite work well. And the reason why I mentioned that is that I can't wait to see what information will come out of the sample. But I was looking at the fact that we needed to create new tools to be able to get access to the content of the canister. But look at the lines here. So here you had, in the last few months, let's see if I can find, there we go. In the last few months, we've been having machinists working on creating a tool to be able to get access to the canister. So here we can see here, they're trying to unscrew this part here. But let's look at this amazing piece of tool. Too often when we think of space exploration, we think of astronauts, we think of probes, satellites going around different celestial bodies. However, we often forget that on Earth here we have teams supporting missions, teams of engineers making sure that everything works well. Rocket scientists. We also have computer technology and communication, making sure that information can go from Earth to the piece of equipment and back to Earth. But here, this is an example where we have technicians, and they spend a lot of time in putting together this tool. And this part here is in one piece, And this is amazing. And we forget that we, in space exploration, we need a lot of tools. We also need people with a lot of knowledge and know-how to make sure that these happens. So I thought it was exciting. I can't wait to see the information we will get from this untampered canister, and that's part of what we're going to see in the months to come. But here, I wanted to share that it's a topic that I am of interest, but also the whole idea that when you think of manufacturing, these are important jobs, not just for space exploration, but every aspect of our society. Quite important. And this is the first topic that we have today on our lives about astronomy, about space exploration. If you've enjoyed this video, please subscribe to our channel. I bring topics about science weekly. This is a new project I've had in the last few months to bring what I know to you, but also giving you a chance to ask questions related to scientific topics. I'm here to learn, I'm here to help you, and together if we learn and we can make science more accessible, this will allow everybody to become better junior scientists, better scientists, so we can make the world a better place. On this, I will wish you an excellent day, and I'm going to actually put here a link about a scientific topic that you will enjoy. I'll see you there. And this is our first topic for our live today. This is kind of exciting. I started the live show in the last couple of weeks, and therefore it's always nice to hear, to see what we can do together. So if you're new to my channel, every Saturday, I'm working on putting together a science show where I'm here to answer questions that you may have from the audience. But above all, I'm using questions that my students are asking me during the week, questions that the students that I tutor have questions with, and it allows me to use the whiteboard here and explain to you what they are. That means that you can learn from me, you can ask questions, and it's like a teacher at home, and it's kind of interesting. And it's an idea I had. Let's see what we can learn together. So let's see if we can set up the next session in a moment. So we're going to talk about optics today. So we have exams happening in Ontario, Canada next week, and some students are having great questions about that. I have several students who ask me about optics, so we're going to talk about this topic. I do like it because it is very applicable. And so let's see what the unit 11 here, production and reflection of light. Okay, so light and reflection. Oops. Perfect. Oops. This is the French version. Let's see if I can write it in English. So what's a good idea? Reflection. Okay. Perfect. Do you have any, let's start again. Do you have any idea of what light is? We know that with our eyes, we can see different objects. We can see the light from the sun. We can see lights from a source of light energy, you could say. But we also know that sometimes, over the years, sometimes our eyes either don't see as well. Second, we also know that sometimes people don't see all the colors. But can we also use light to better understand the physical world? And this is the first video here on a series about optics. So let's see what we can learn here. So when you think of light, the first thing we can think about is about our eyes. Our eyes are biological pieces of equipment, you could say, that are fine-tuned to receive information, magnetic information that our eyes are accepting. They are also, how can I say that? They are interpreting, and they're sending it to our brain. And our brain are looking at the information, the input, and can tell us what is the object, the color, and so on. So this is something that we grow throughout our lives. We gather more data. We know better what it is. But what is this light? what kind of energy it is. So let's see if we can talk about it a little bit more. So I have here, there we go. Excellent. So this is what we call the electromagnetic spectrum of light. Let's see if I can put the link into here into the chat section. If you're listening to this, watching this video in replay, the link will be in the comments below. So here what we have, it just shows that we have basically a visible light right here. So that means that we have our eyes that can see red colors. We have yellow, green, blue, and purple. So you can see this is a very small bits on what the whole spectrum of electromagnetic energy. So here, this is what we call visible light. So that means that when we think of electromagnetic waves, it's much more than that. However, our eyes are specialized to be able to see those only. So let's see if we can explore that a little bit. If you have visible light, they're made by light bulbs, for example. We also have visible light coming from the sun. Now, we also have different kind of energy considered as part of the electromagnetic wave. First of all, we can go, so if we have wavelengths, so here the wavelengths of visible light are 10 to the power of -6 meters, so like a millimeter in length or so, between 0.4 and 0.7 millimeters. So what is interesting is that those waves can actually get longer and longer. So if we have longer waves from the visible spectrum of light, we have what we call the infrared section. Infrared light we cannot see with our eyes. However, we can feel it. If we're close to a fire, we can feel the heat coming towards us. So these are longer wavelengths. So here for the infrared, we have at the 10 to the power of -5. So here we have a few centimeters in length. Now, interestingly enough, we have here different sources. So we have a heat source. If you get shorter wavelengths compared to the visible wavelengths, we have what we call ultraviolet. Now, the ultraviolet wavelengths are much shorter. We cannot see them with our eyes. However, if we go into the sun, sometimes we can feel it on our skin. We can feel the heat from the sun as infrared energy. However, the UV, often the way I see it is that when the sun comes to your skin, and it's just like needle poking on your skin. So there's a reaction there, much shorter. So what happens is that they can make some molecule vibrate. So here the wavelengths are 10 to the power of -8. So what happens is that much shorter wavelengths, that means that molecules are affected by those wavelengths. And that's why if you go to the light with too much UV light on your skin, the molecules are vibrating, they break down, and therefore we have mutations in our DNA. And what happens? We can have a skin cancer. So we have to be careful. Now, if we get the wavelengths shorter and shorter and shorter again, then we can affect a much smaller matter. So here it goes to, we can affect the atoms and we can affect the nuclei. Now here we have X-rays and gamma rays. Now, if you think of X-rays, X-rays can be used if you go to the dentist. So let's see. So here's an example. So this picture here is from here a person from Dutchland, and here it's their own picture. I'm going to put the link in the comments once I edit the video. And what is interesting here is you could see the density of the matter can change. So here you could see we have a tooth that has been repaired. The ceramic used is much denser than our teeth, and that's why the X-rays don't traverse them. And you could see in the root, we can see here the root of the tooth, and here we could see the person had a root canal. So here the wavelengths are much smaller, much higher energy. Too much X-ray is not good for us because it affects atoms, and then it could create also difficulties with our DNA and mutations. Now, on planet Earth, we are protected from the X-rays from the sun, for example, because we have our atmosphere, and the molecules in the atmospheres, the molecules are absorbing the X-ray wavelengths, which is good for us. So now if you go and make the wavelengths a bit longer and longer, so we're going through the infrared. So now we go into what we called microwave. So the microwave here, so here we have radar, and we use those to see energy coming from our space. So here you could see that we have wavelengths of 10 to the power of -1 to 10 to the power of -2. So here we have 0.1 meter, so wavelengths about this big here. And the reason why those microwave need such a big radar dish is because waves are getting bigger and bigger the further they get away from a star. So let's see if I can show you. So for example, if you have a star right here, the star is sending waves of energy like this. So that means that if we have our planet that is right here, let's see, this is Earth, we are receiving wavelengths from our star. However, if you are looking for information from a distant star, then we have those waves that are getting longer and longer. So what happens is that if our Earth is at so many light years, tens of thousands of light years, then the wavelengths it's much bigger. And this is one of the field of research I love in astrophysics. So here's an example where we have a satellite dish that is being used to collect data from far stars. Now, in the last few years and decades, more and more of these have been created. So here, this is about 50 meters in diameter. However, it has a weight, and we have to find a way to, there's a limit to the structural integrity of these. One of the best project I like, it's called the FAST project. It is a satellite dish that is in China. So what they did here to make it as big as they could, they actually have a suspended dish between mountains. So here the FAST project, called FAST, is in China. And here the diameter is about 500 meters in diameter. So that means that we can see much larger wavelengths. That means that we can see stars and information from stars coming from further and further away, especially people interested in knowing about stars, but also the origin of the universe. And that's beautiful this way. So here we have, so this is a picture from Rodrigo con Lage, and it was done in 2020. That's a project that is not very old. So if some of you, sometimes they can teach, they can speak in English, but also in Mandarin, excellent opportunity for you to work with them. Outstanding possibilities. Excellent. So let's see if we can go back to my, perfect. So here, interestingly enough, so we have microwave, then we go into the radio wave. So the big dish I showed you with the FAST, for example, you have radio waves that are longer and longer. And here we have all the way to AM radio waves. So here these waves are 100 meters, 1,000 meters in length, much bigger. So we need bigger and bigger radio telescopes to do that. Now, I noticed that there is also some projects around the world. Sometimes you can use, there's a few projects where people were using satellite dish of different individual, because keep in mind that if you are part of a city and you have 1,000 people with the satellite dishes pointed in the same direction, why can't we take all these satellite dish and use them to receive information from space at a diameter of a kilometer or even more. This is quite exciting, and with the internet, that's getting more and more possible. Perfect. So this is the electromagnetic waves. So the electromagnetic spectrum of all the sources of energy. I remind you that the visible light is only a small portion of what the electromagnetic wave or spectrum is, but by learning how visible light works with our eyes, we can better understand every other types of waves, and that is why we are studying optics in grade 10 in science. If you've enjoyed this video, please do not hesitate to subscribe to our channel. I bring in some videos about science weekly. I'm here to answer your question above all. If it happens you have any clarification questions, don't hesitate to put them in the comments below. In the meantime, my name is Alain Faber. I've been teaching science for more than 25 years. I'm here to share what I know and also do science with you. So at this point, I'm going to link you to another video that you will enjoy so that we can do more science together. So there we go. First video of the day in optics, and let's see what else we're going to learn together today. So this is my second show. No one has showed up yet. I'm kind of feeling relieved because it is going out of my comfort zone, but as we go along, my shows will be better and better, and that I know because the more you do something, the better you get. So let's see what the next topic will be. So let's see. So light reflections. Okay, and then light reflection. Okay, let's do it that way. Perfect. So there we go. Do you ever wonder how come you can have a perfect reflection of an image? So here I have an example of Lake Louise in Canada. We have the mountain up here, and the mountains here, the light is reflected on this flat surface of Lake Louise. No ripples. We have a perfect reflection of what is happening here. You can see the trees and the trees down here. So this is a perfect reflection. So how is light working so that we can have such reflection? And that's what we're going to work with today. So first of all, if you want to have a chance, I'm going to put a link here to the last video about what is light. And light is part of an electromagnetic spectrum. Our eyes are specialized in gathering specific wavelengths of that electromagnetic spectrum. So here we need to know, how can we study that light? So the first thing we have to keep in mind is that if you have a light source, so let's see, I have a light source here. So I have a candle. That candle will have light. And light goes in all directions. So if you're in a party and you have a candle, the person in front, at the back, or on the side will all be able to see the light. Interestingly enough, light always goes in straight line, given what's happening on planet Earth. That means that if I have, for example, an object right here, a human on the other side would not be able to see the light because the electromagnetic waves are being blocked here. So here we will not be able to see the light. I know that some of you would say, well, if you look at stars, we know that the light of some distant stars sometimes can change direction when there is a black hole. I do understand that, but we're not talking about high energy physics here or black holes. If you're interested, put your comments below or your questions below. I'd be more than happy to answer you. So the question we have here is that if you take this light this source of light, we have an infinite number of electromagnetic waves going in all directions. So the question here is, how can we study light a bit more? The best way to do is that if I can, from a source, from an infinite number of rays, if I can find a way to focus only on a few, or focus on one, can this help me? And the beauty with that one is that if I can figure out what this light ray is doing, that will give me an idea of how this light wave would go, how this light waves would go, as well as all of these other ones. So when we are studying light in optics, in physics, instead of looking at all the situations, we're looking at one light ray or a few light rays and try to figure out what we can learn. So if we take this light ray here and we take a few that are beside, if we figure out what one light ray does, we can figure out what 8 does, and then we can put it in the 3 dimension, and then we have a good idea of how it works. So here I used a candle where light can go from all angles. Now, how can we get something that we can call a laser? A laser is interesting. A laser is usually a box where we have a light ray. Oops, let's see if I can, like this. So a laser would work where you have a little hole here where the light ray can go this way, and you may have a few that can go in. But what is interesting is as it goes in the box, on one end here you have a curved mirror. On the other end, you also have a curved mirror. So what happens is that all of these will be reflected. And then what happens is that you have lights that are being reflected over and over again, up to a point where it will all focus in one part right here. And then we have a specific, more condensed ray of light. So we have a source, and then inside the laser, there's a way for it to accumulate energy to a point where we can actually have a strong laser here. Often we think of red lasers, but you can also have blue lasers that have different wavelengths, and we can do different things from them. Now, if we can study one ray of light, that could tell us so much more about what's happening in physics. So let's see if we can look at what happens when you have light reflected on a surface. So let's see. Okay, so we have this way. We have this way. Actually, I'm gonna do something. This. Okay. In physics, when we talk about mirrors and rays of light, we often represent mirrors like this, where this is a flat mirror and this is the back of the mirror. This is a mirror that is not even, not flat. So what happens is that when we have rays that are going on the surface of the mirror, we're going to have reflections like this. So if we have this going this way, we're going to have reflection here. If we have another one here, we're going to have reflection. Now, earlier in this video, I showed a picture. So if you take up this picture here, we have light coming from the peak of this mountain. It's going reflected on this lake right here, and then the light comes to our eyes, which is interesting. So if you were to take this peak right here, this is a different point on the lake, and it comes to our eyes. These green trees here, they're going to the part here, and they come to our eyes. So when you're in art and you have a point of perspective, this is often something to keep in mind. Perfect. Now, what happens if you have an uneven surface of light? So that means that you have here some of the light could be going back. Another one here, the light would go this way. This one will go here. This one will go there. So when you have an uneven mirror, or if you take, for example, you go to a lake and there's wind and the surface of the lake is uneven, you cannot really see reflection on its surface. You need a very flat surface to help us reflect the light. So is there a way to see the theory behind that? So that's what we're going to do in one moment. So let's see. So we have this. Perfect. So we're going to do this way. Perfect. Let's see if we can look at some vocabulary that could be useful. So that will be the reflective surface or a mirror. Is there one or two R? That's a good question. We have, so this is a plane mirror with two R's. Perfect. So when you have a plane mirror like this one, and we have a ray of light coming this way, it touches a point right here. So this is what we call an incident ray. So this is an incident ray. We talked earlier about the fact that if you have a light source, you have tons of different rays going through. Here we were looking at one only. So we have an incident ray. So the light is going this way. Now, what is interesting when you think of this ray right here, there is an imaginary point that gives us a vector right here. And this is called the normal. The normal, do you put an E in English? No. So the normal is what? It is an imaginary line perpendicular to the reflective surface or the plane mirror. And it gives us an angle. It gives us this angle right here. We put a little I right there, and it's called here an angle of incidence. Angle of incidence. So here, this is the first part of our drawing. Now, what is interesting is that if you have light going this way on the plane mirror, we know that it's going to be reflected. But here the theory goes well. It shows that when we have a light ray going this way, it is being reflected this way. And this is called a reflected ray. Perfect. And interestingly enough, we have here another angle, and we call this one an angle of reflection. Angle of reflection, like this. Okay. So this is the base of pretty much everything we do when we have mirrors, when we have also refraction. It's going a bit beyond, but still the basics here of what we have is very important. So we have a plane mirror, we have an incident ray that is being reflected. Here we have an imaginary point, and we have here a line that is perpendicular that we call the normal. That is important because we have an angle between the normal and the incident ray that gives us the angle of incident, and then the reflected ray here will have an angle between the normal and this reflected ray. Interestingly enough, when we have a plane mirror, is that the angle here of incidence equals the angle of reflection. And that's interesting because if you look at what we have here later on, as we progress, you will notice that if you put something like this, you have little triangle here and triangle there. And therefore, if we have triangles that are right triangles and we have angles, that means that we can use trigonometry to solve some of these problems. And that will be what we're going to study in the days to come. Some of you will say, well, trigonometry, I don't like it, but you'll see, you can look at all the trigonometry and you can simplify it to a point where it becomes very simple. You will see. If you've learned something amazing so far with respect to the reflection of light and its theory with the incident ray and the reflected ray, the angle of incidence, the angle of reflection, and the normal, please do not hesitate to subscribe to our channel. I bring in some topics about science as much as I can. I use these topics from your questions from my students or the students that I tutor, because I love to share what I know and hoping that once you understand better, you will be able to succeed better. And that is part of how we can be better at school. On this, I'm going to put here a link to another video that you will love, and I'll see you there. And that is our second video about light reflection. Perfect. I've talked about this part here. The next one we're going to talk about will be how we can have, let's see, images on plane mirrors. You'll see it's fun. This is quite a big, so I'm going to put it here. Maybe we'll be able to take a picture, so that will be a great thumbnail. Let's see. There you go. That's much better. Oops, this way. Very nice. I'm going to erase this to lead to our next idea. Okay. So let's see, can we, nice. Perfect. When you go to a party, have you seen these disco balls like this? The disco balls are made of tons of little mirrors that are all flat, and they are glued on top of a sphere. What is interesting is that every little mirror is a plane mirror, but because it's on a curved surface, it allows us to have light, and it makes amazing patterns in our party space. Now, how does this work? It is when we use the theory behind the reflection of light on plane mirrors. So let's see if we can answer that for you, and let's see if I can show you example to help you trace images of objects with plane mirrors. So let's see, stay with us. Okay. Okay, so we have, let's see, plane mirror. Let's see. Okay, can we see it nicely? Perfect. So let's review the theory we have about the reflection of light with plane mirror. We know that if we have a plane mirror and we have a light ray, a ray of light going towards our mirror here, we have what we called an incident ray. Incident ray. We also know that where this ray touches the mirror, we have an imaginary point that leads us to a vector, and that vector is called normal. The normal is at 90 degrees with respect to the plane mirror. The reason why the normal is important is that when you have this incident ray touching the mirror here, we have the slight ray that is being reflected. This is called the reflected ray. So we have a reflected ray like this. Now, this brings us to two other concepts that are amazing. The first one is about what we call the incident, the angle of incidence, and the other one is angle of reflection. So this one here is angle of incidence, and this one here is angle of reflection. So what we have here is that we have these two angles that are exactly the same. So let's see if I can write down this vocabulary for you. So we have angle of incidence and angle of reflection. The idea here is that the more we understand the principle behind these concepts, the easier it is to understand, the better you will succeed at school. The whole idea here is that my beliefs is that once you learn something and you can put it into action because you understand it, that's when you have some transformational understanding of what science is, first of all. But second, succeeding at school can be tough for some, but once we understand, it makes life so much more fun. So here, this is the theory behind the reflection of light. Now, from here, what can we learn? If I have an object in front of a mirror, then there's an image being done. So, for example, take a moment, pause this video, go into you can go to the washroom, or if you have a mirror, look at yourself in the mirror. You know that you are a human being with a body, a physical body. You have a mirror in front of you, but the mirror shows you as a reflection. But you also know that you are located behind the mirror. So you cannot touch the image because it is behind the mirror. If the mirror is on the wall, it's as if you were in the wall. But you know that the image exists because you can see it. And you know that your body exists because you're here. The whole idea is, how can we trace the image of an object using light rays? And that's what we're going to do together. So let's see. Oops, there's no more juice here. So this is the symbol for, let's see if we can have a focus. Let's see. Perfect. So here, this is the information I have for my mirror. It is a plain mirror. And let's see if I can we're going to do something that is easy. Let's do a pen like this. Perfect. We know that this is an object. The object is a physical object. So you could take a marker like this. It is in front of the mirror. But you also know that there is somewhere behind the mirror an image. And the question is, where is that image? In order to do that, we need to trace light rays. So what I'm going to do, I'm going to take a light ray that will go here through the tip to the mirror here. But we know that when the light ray reaches the mirror, which is a flat surface, we have an imaginary line, which is the normal. And that normal tells us where the reflected light will be. And the reason for that is that we have the angle of incidence that is equal to the angle of reflection. So this is a light ray that is coming from the tip here and is reflected. We also know that when we look at an image, it is behind the mirror here. So the light that goes here is reflected. So that means that there is an imaginary line that we can find behind the mirror like this. That brings us to a second line. So if I take another line and I go from here to this point right there, this brings us to a point, which is an imaginary point from which we have the normal, like this, and for the normal. But we have a reflected ray, and we have, so the ray is going this way, it's being reflected this way. And then we have here the angle of incidence equal the angle of reflection. But interestingly enough, this is reflected on the real world, but we have an imaginary line that could be at the back here as well. Let's do another line that is interesting. If I have a line that is going like this, that is perpendicular to my plane mirror, this ray is in line with our normal like this. So that means the angle of incidence equals 0. That means the angle of reflection also equals 0, and therefore the light that goes towards the mirror will be reflected on that plane. But that also means that there's an imaginary plane, an imaginary ray that is going behind the mirror as well. Now that's interesting. I made here 3 lines. We have here the 3 rays of light that are meeting at this point. Interestingly enough, we have also 3 lines crossing at the back here. And that's quite important, because if the three rays meet here and the 3 rays meet there, that means that my image will be right here. And we can actually find the exact location of that image. Now, often in my class, people are saying, yeah, but you put 3 rays and they met there. And therefore, it's always easy because you make it look easy. That's possibly true. But what if I was to use any other light rays? If my light ray was going here, it would be reflected there because of the normal. Oh, it does meet at this point. If I have this ray that is going here, we have ray of the incident ray, the reflected ray, they are meeting there as well. So it doesn't matter really what angle you're using. You need to look at specifically how is, in this example, where the light is reflected, where the light is reflected, where it is reflected, where it's reflected, always using the same principle. If you have a flat mirror, you have an incident ray that will touch the mirror here. At this point, you have a normal that is perpendicular. You have the angle of incidence that equals the angle of reflection, and we have a reflected ray. So this part here is the theory that was applied here, 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 and here. And that is how we know that if we have an object here, we have an image at the back. Now, interestingly enough, there's some other information we can figure out. The first one is that if you have here an object like this, you have a distance between the object and the mirror, and that becomes the distance of the object. So the distance between the mirror and the object. But that also means that you have a distance of the image. The distance of the image, di, is the distance between the mirror and the image. Other things to keep in mind is that you have here the height of the object here. The height of the object here is from the bottom to the top. Interestingly enough, if you go at the back here, you also have what we called the height of the image. So here you could see that we can actually start measuring entities. We can measure some specific characteristic of the object with the height and the distance from the mirror, and characteristic of the image here from the height of the image and the distance of the image. And that becomes important because in the next few videos, I'm going to share with you how this information can be used when we have curved mirrors. So let's see, before we finish this video, if I can give you another example of how this works. Basically, how you can trace where the image is. So let's see if I can do another example. If you've enjoyed the video so far, my name is Alain Faber. I've been teaching science for more than 25 years. There you go. I am doing these videos for my students, for students I tutor, but also from anybody that will be looking for how to better understand science. I use questions from my students and students I tutor to find ways to have great videos, but also from your comments. So if you need any answer to one of your questions, put the question in the comments below. If you have any clarification questions, put your clarification questions in the comments below, because I always read them, and that gives me ideas for future videos. So let's see if we can look at another example with a plane mirror. So here I'm going to trace my plane mirror like this. Perfect. I'm going to give so often, so why not? So I'm going to give an example of, let's see. It will be an object that is at an angle. So we're going to have, what can it be? Let's see. So we have like this. We have a house like this. What I want to do is I want to be able to figure out where the house is. So here, what I need to do is figure out, this is the object. This is an image that will be behind the mirror. Now, I'm not going to do all the points here. So what I'm going to do is I'm going to take some this away, comes to C. So I'm going to look at 3 specific points only, but you could do that for other points if you wanted to. I'm going to do the tip of this roof, the edge of this roof, and the base right here. That will be how I will find where the image is on the other side. So the easiest way to do is that if you take a ray that is perpendicular, so let's do it this way. So we have a ray that is perpendicular to the mirror. We have our normal, and therefore we have a light ray that is going back this way. So that means that we have a ray that is in line with the reflected light. I'm going to do another ray of light. So here's another incident ray going this way. We have our imaginary point here. We have a perpendicular line right here. That means that we have a reflected light like this. And that means that if you go here, you have the intersection at the back here. So I'm going to do a third line, but for the other 2, I'm going to just do 2 because the drawing will get crowded. If I was to get, let's see, a light ray that will go like this to this point, we have our normal, the angle of incidence here equals the angle of reflection, and we have here the reflected light, and here we have the 2 lines that are meeting right there. So that means that we have here 3 rays of light, meaning at this point on the object, that means that the 3 rays of light that are meeting here will be the meeting point for the image. So these 2 points will be the same. So that means that what we can do for the other 2. So if I have this one right here, so let's do a ray of light going this way. Then we're going to do the same principle. We have a normal right there, and then we have the reflection right there. So the reflection goes like this. If we have, let's say, a ray that is perpendicular to the plane mirror like this, so the rays goes this way. We have a normal that is right here. The angle of incidence and reflections are both equal to 0. that means that the ray will go back to the same place. And this is where they will meet. I could do a third line here. So if I was to do a light going this way, being reflected, they would meet to this point. Now it's interesting because we have 2 points for the objects, and now we have 2 points for the image. So that means that if I was to link these 2 points like this, that means that I have this first side of my house. So let's see if I can do another one. So let's take pink for this one. I have my third point. I'm going to go here. We are perpendicular to the mirror. We're going to go this way. Angle of incidence equals 0. Angle of reflection equals 0. That means that the light will go back. And we have, so the light ray goes in. When it goes away, this is the imaginary line going behind the mirror. If I am to go this, let's see, we have a line right here. Oh, my mirror is not long enough. So this light ray touches my mirror. I have here my normal, which is perpendicular. We have the incident ray here. We have here the reflected ray with the angle of incident equal the angle of reflection. And here we have the ray that is extended at the back. So here we have an intersection point here. Let's see if I can get purple. The intersection point is right there. So here, so my drawing is not up to date, up to scale. But here would be where we have our house there. How was I able to figure out where the image of this object would be behind the mirror? I do the light rays for the plane. Now, if you look at this one, you're going to say, oh, this looks so complicated. It may look like complicated, but if you break it down into simpler steps, like the theory behind the reflection of light with an incident ray, reflected ray, where the angle of incidence and reflection are equal. So this complicated drawing, if you look here, you have one small part. We have one small part, one small, one small, one small, and one small. We are taking one ray at a time, and you can bring back, so you can go on the video and go back a little bit and look at how I traced each of these. And this allows me to trace the image of an object when we have a plane mirror. And as I mentioned before, if I take some of these away like this, so from this point to the mirror, I have the distance of the object. Here I have the distance of the image, and they are the same. We have here the height of the object. So I put a little O here for object, and we have here the height of the image. I stands for image. The whole idea here is that you can start putting measurements for here, and that's how we can use more and more what we know about light to make this happen. So this is my second video on how light is reflected. Hopefully you've enjoyed this. If you have any clarification questions, put them in the comments below. I'm going to read them. I always look at your comments and your questions to bring the next video. On this, if you've enjoyed, please subscribe to our channel, and I'm going to put here another video that you will enjoy. So there we go. So this is our second video. Perfect. So let's see what I want to work on today. Okay, so the next one is curved mirror. I think I'm going to do curved mirror. Let's see. Curved mirrors. So that's the next thing, and we have calculations if we wanted to. Okay. So I think this will be the end of our stream today. I did 2 videos on optics. If you have any questions, clarification questions, put them in the comments below. I always look at them. And next week, I'm going to add more videos on reflection of light. And don't hesitate, I'm here to help you, because I know that once we understand better what we learn, it's so much easier to appreciate what we do in class. And you know what? This is what we call transformational. And I do believe in you. On this, having a wonderful day. I'm going to see you next week at noon next Saturday. Take care. Bye-bye.